Note that the existence of the limit in the alternate form requires that the one-sided limits, the limit as x approaches c from the left and the limit as x approaches c from the right, exists and are equal, right? The limit has to exist. So if it's continuous, the limit from the left has to equal the limit from the right. It says these one-sided limits are called the derivatives from the left and the derivative from the right. So again, if you have that negative sign there, this would be the derivative from the left. If you have that positive sign there, this would be the derivative from the right. It says it follows that f is differentiable on a closed interval a to b, when it is differentiable on the open interval a to b, and when the derivative from the right at a and the derivative from the left at b both exist. When a function is not continuous at x equals c, it is also not differentiable at x equals c. So that's something that's important. Not continuous means it's not differentiable. Okay, differentiable means continuous, not continuous means not differentiable. It says, although it is true differentiability implies continuity, so if you can find the derivative, you know it has to be continuous, the converse is not true. So you cannot say you are continuous at a point, you have to be differentiable at a point. So if your derivative exists, then you're continuous. But if you're continuous, you don't necessarily have a defined derivative. So that's all that's trying to stumble through. It says the greatest integer function is not differentiable at x equals 0 because it is not continuous at x equals 0. So here's x equals 0. This is the greatest integer function. Remember, you're just rounding down to the closest integer. Round down is what that one always is. And if you look at x equals 0, the limit from the left is not equal to the limit from the right, so it's not continuous at x equals 0. The limit from the left is -1, the limit from the right is 0, right? Not the same number, not continuous. If it's not continuous, it's not differentiable. So that's what they're getting at right there. But what you could do is look at it potentially from, well, I don't want to get into it too much. I don't want to confuse you any more than that. All right, so example 6, again, an interactive version if you want to download that and plug it into the Wolfram CDF player. If you're a nice visual learner, that will help you out. It says determine the derivative of f of x equals the absolute value of x minus 2 at x equals 2 if it exists. So let's take a look and remind ourselves. We've seen this function several times in the limit sections. We saw this in the different review packets that we've done. We need to be comfortable with handling the absolute value of x minus 2. Remember that the absolute value of x minus 2 is really a piecewise defined function here. You have f of x equals the absolute value of x minus 2, but what we have is this is really two different functions. Remember, anytime that this inside right here, x minus 2 is greater than or equal to 0, so let me solve that real quick. Anytime x minus 2 is greater than or equal to 0, which tells me that adding 2 to both sides, anytime that x is greater than or equal to 2, so if x is greater than or equal to 2, it returns the exact same thing. If the inside is positive or 0, the absolute value function returns the same thing. So that would be the function x minus 2. And anytime it's not that, so if x is less than 2, that means the inside x minus 2 would be a negative number. And if the inside is a negative number, it returns the opposite. So that would be the opposite of x minus 2, negative, and then in parentheses, x minus 2. So we have two different functions that we're dealing with here, okay? So the question then becomes, what is the derivative of this function? Well, we could look at it from both sides, looking at it from the right and looking at it from the left. We can see what's actually going to happen here. So if you use the book's definition, it's actually really not too bad using the differentiability and continuity. What they say is the alternate form. So what they want is the limit as x approaches c of f of x. So let me write it down real quick. The alternate form. This is not the one that we use, but this is the alternate form. Okay. This is the limit as x approaches c, which in this case is 2, of f of x minus f of c all over x minus c. So that's the idea, is you can use this alternate form that we just covered. Okay, so let's try it first from the right. So what we're doing is we're looking at the limit as x approaches 2 from the right, and notice from the 2 from the right, we'd be talking about greater than or equal to 2, so we'd be using the function x minus 2. So this would be f of x, which would be x minus 2, minus f of 2, which would be the absolute value of 2 minus 2, which is 0, all over x minus 2. Well, in this case, this is the limit as x approaches 2 from the right of x minus 2 over x minus 2, which is quite simply the limit as x approaches 2 from the right of 1, because those simplify, right? So, and the limit of a constant is a constant, so that would be 1. So the derivative from the right is the number 1. Let's look at it from the left. So let me write from the left here. From the left would be less than 2, so we would be using the function as negative quantity x minus 2. So this would be the limit as x approaches 2 from the left of f of x, which in this case is negative x minus 2, minus f of c, well in this case f of c is f of 2, which again is 0, all over x minus c, which in this case is 2. Remember, you're evaluating this at x equals 2, right? So this would be the limit as x approaches 2 from the left of negative x minus 2 all over x minus 2. The x minus 2 simplify, and we end up with the limit as x approaches 2 from the left of, well, it's just a negative 1, and the limit of a constant is the constant, so that's negative 1. So what do we notice? The limit from the right, which is, it's truly the derivative from the right with the formula that we've used, is 1, and the derivative from the left is negative 1. And since those two things are not the same, they don't agree, that tells us that the derivative doesn't exist. At x equals 2. Now that doesn't mean the derivative doesn't exist anywhere else. In fact, the derivative does exist everywhere else. It's just at this point. So again, I'm a visual person, so I want to see what's going on here. I want you to think about that graph, and if you need, go ahead and use Desmos to graph this for you. What's the absolute value of x minus 2 look like? Well, it looks like a V, right? And here's the value of x equals 2. And what you're looking at is the slope on this side of the line is a positive 1, and the slope to the right, right? And the slope on this side of the line to the left is negative 1. And at that point, when you look at what happens at that point, from the right you have a different value from the left, so you would say the derivative does not exist. It does not have a tangent line, right? So there's no straight tangent line that we can use. So if there's no tangent line, there is no derivative at that point. So just kind of a big picture idea, anytime you have a sharp V where it comes together in a V, the derivative is not going to exist because the left and the right don't agree.